Hey everyone, and welcome to this explainer. Today, we're going to be talking about the invisible strings that literally hold our modern world together. I'm talking about satellite communication. You know, it's this hidden, massive infrastructure that powers our everyday lives, keeps us connected when local networks totally fail, and actually is serving as one of our absolute most crucial tools in the fight against climate change. So let's jump right in.
Okay, let's start by posing a really fundamental physical problem. Seriously, have you ever stopped to wonder how we instantly talk across a completely curved planet? I mean, radio waves want to travel in a straight line, right? So, how exactly do you send a signal from New York to Tokyo without it just shooting straight off into the atmosphere? Well, engineers faced this literal wall when they first tried to build global communication systems.
To unpack this, here's where we're headed. First, we'll look at how we defied the Earth's curvature. Then, we'll map out the 3 mini-orbital zones, track the actual journey of a signal, dive into space tech for climate action, and wrap up with future trends and challenges.
All right, part 1, defying the Earth's curvature.
So, for a long time, our terrestrial communication systems hit a hard physical limit. If you're relying on traditional ground or skywave propagation, you're pretty much capped at around 1,500 kilometers. The Earth curves, obviously, and the atmosphere can only bounce a signal so far before it just completely weakens or scatters. But what if you put a massive microwave repeater high up in space? Suddenly, you completely bypass those ground obstacles. It was a total game changer. We unlocked true global coverage.
And this massive reach creates what engineers call a footprint. Basically, that's just the specific coverage area on Earth where a satellite signal can be picked up with practical strength. And here's the cool part. As long as any 2 ground stations are inside this massive footprint, they can instantly exchange information. It doesn't matter if there are oceans, mountains, or massive deserts sitting between them.
Moving right along to part 2, the 3 orbital zones.
Now, let's look at the specific neighborhoods in space where we actually park these incredible machines. It's so fascinating because a satellite's altitude perfectly dictates its job. It's like a cosmic zoning map. We've got 3 main zones. Down low, between 160 and 2,000 kilometers, is low Earth orbit, or LEO. Being that close means low latency, which is perfect for fast internet and detailed Earth observation. Move further out to medium Earth orbit, or MEO, and you hit the sweet spot for global GPS and navigation. Finally, way up at 35,786 kilometers is geostationary orbit, or GEO. At this exact height, satellites rotate exactly with the Earth, making them look perfectly stationary in the sky. That makes them ideal for stable TV broadcasting and constant weather monitoring.
But of course, that massive distance for GEO satellites comes with a bit of a physical tax: 240 milliseconds. That's the exact round-trip time delay it takes for a signal traveling at the literal speed of light to reach a GEO satellite and bounce back down to Earth. It's a tiny fraction of a second, sure, but if you've ever experienced one of those super awkward lags during a live news broadcast, well, that math right there is exactly why.
But being up that high doesn't just mess with our ping times. It also triggers something astronauts call the overview effect. Have you heard of this? It's this profound shift in cognitive perception when looking down at Earth from space. Seeing this fragile, rocky ball completely adrift around the sun creates a newfound appreciation for its wonders. And honestly, I think this perfectly bridges the cold, technical mechanics of satellites to a really deep environmental awareness.
Okay, part 3, the journey of a signal.
So how does a simple text message or video feed actually survive the brutal trip into the vacuum of space and make it back down to your phone? Well, it happens in a very precise 3-step loop. Step 1 is the uplink. That's where an Earth station beams a high-powered, high-frequency radio signal straight up into space. Step 2 happens inside the satellite itself, where the signal is caught, amplified, and, this is crucial, shifted to a completely different frequency. And then step 3 is the downlink, which is blasting that processed signal back down to a receiving station on Earth.
Let's zoom in on that second step for a second, because this is the true heart of the satellite, the transponder. You see, a transponder isn't just some shiny piece of metal acting as a mirror. Satellites are active amplifiers. The transponder catches that weakening uplink signal, injects it with fresh power, and shifts its frequency so the incoming and outgoing waves don't clash with each other. It's literally actively keeping our signals alive over thousands of miles of empty space.
And believe me, engineers leave absolutely nothing to chance here. This formula is known as the link budget equation. Basically, received power equals output power, plus your gains from amplifiers and antennas minus the free space path loss.
Now, don't worry, we aren't going to get bogged down in the math today, but this equation just shows how meticulously engineers calculate every single ounce of power gain and loss. They literally have to, just to guarantee that your navigation map or FaceTime call works flawlessly when that signal finally hits your device.
Which brings us to part 4, space tech for climate.
Now that we understand the incredible engineering behind how these systems work, we really need to look at how this invisible infrastructure is being actively leveraged to save our planet. Satellites are quite literally our eyes in the sky for environmental monitoring. They're up there tracking greenhouse gas concentrations, monitoring ocean color changes to spot algae blooms, observing shifting biodiversity levels, and giving us rapid detection of wildfires and floods. The sensors mounted on LEO and GEO satellites are, without a doubt, our absolute best tools for accurately modeling and understanding climate change right now.
And you know, it's not just the dedicated observation satellites doing the heavy lifting. The Global Navigation Satellite Systems, or GNSS, parked way up in MEO, are putting in the work too. The exact same GPS technology that helps you navigate rush hour traffic is simultaneously providing super precise geospatial positioning to track melting ice mass levels and tectonic ground shifts down to the literal centimeter. They are out there measuring the absolute most critical vital signs of global warming.
And here's why this matters so directly to humanity on the ground. When extreme weather events like huge hurricanes or earthquakes strike, they almost always wipe out local cell towers and fiber optic cables. In those totally desperate moments, satellites completely bypass the damaged ground infrastructure. They become our absolute, undeniable lifeline to coordinate emergency communications and critical rescue operations. But what's truly inspiring to me is how space exploration has historically driven global diplomacy and environmentalism. I mean, it really started back in 1968. That famous Apollo 8 Earthrise photo essentially kickstarted the entire modern environmental movement. Fast forward to 2021, and we have NASA and the European Space Agency signing a joint intent for climate action. Then in 2023, China and France jointly developed an oceanography satellite. This proves that, hey, while things might be incredibly tense down here on the ground, international cooperation actively thrives up in orbit.
All right, let's head into our final section, Part 5, Future Trends and Challenges.
Let's take a look at what's on the horizon for satellite connectivity. And honestly, some of the very real dangers we face as space gets insanely crowded. The future of connectivity is absolutely exploding right now. We're seeing the launch of these massive mega constellations of LEO satellites by companies like SpaceX and Amazon, which are promising to finally bridge the global digital divide. We're also integrating satellites directly into our 5G cell networks. Those are called non-terrestrial networks. And to handle all this massive traffic without stepping on each other's toes, the newer satellites are using highly precise laser-based optical crosslinks instead of traditional radio frequencies to shoot data between each other in space. It is wild stuff.
But as you can probably guess, with thousands of new satellites launching, it is getting incredibly congested up there. And that is exactly where regulators like the International Telecommunication Union, or ITU, have to step in. They have this monumental task of managing global frequency bands so these satellites don't just jam each other's signals all day. But more importantly, they are desperately fighting to tackle the growing risk of space debris. They're working so hard to keep our vital orbits from becoming a chaotic, dangerous junkyard.
Really, it all comes down to this super delicate balance. We deeply, deeply rely on satellites for both global internet coverage and for tracking our fragile climate. But orbit congestion directly threatens that balance. The very same technology that's empowering us, and quite frankly saving our planet, could literally be choked out by its own rapid, unregulated expansion.
So, as we wrap up this explainer, I want to leave you with something to really think about. As we rush to launch thousands of new satellites to connect every single inch of our world, are we risking the very space environment we absolutely rely on to survive? Thank you so much for joining me today. I really hope this explainer leaves you eager to look up and learn even more about our vital, invisible future in space. See you next time.